Hello guys, so today we will discuss the system design for ride sharing apps like Uber, Rapido or something like that. Uber, let's say Rapido, or basically in general ride sharing, driver rider kind of apps. Driver apps. So yeah, we won't waste much of our time. This is one of the good question of the system design where we can discuss hell lot of things. So yeah, without wasting a much of time, let's directly go into the functional requirements. What we want to build, because Uber, Rapido, this kind of app are huge. People can do many things out here, right? But what we want to design our system, we need to keep it crisp and simple for our 45 minutes or 1 hour round. So coming on to the functional requirements. The functional requirements are basically what all features you want to develop in your system. So yeah, when we talk about the Rapido and Uber, let's see how the user flow actually goes. So whenever we open app like Uber, it initially asks us to put the location where we want to go, right? So it already knows our pickup location. It wants us where we want to go. We call it drop off location. And when we click on like yeah, move next, so it gives us the estimated fare about the different things. Either you want to go via bike, if you want to go via auto, it will give you the price via cab and similar. So the first function should be user should able to see user should able to see estimated fare, right? Estimated fare based on pickup and drop location that he will be inputted. So this should be first functional requirement that our system should do. Other thing is, when we have the lot of options, like we can select any of the option and like request our ride. So user should be able to request a ride based on all the available option that we provided him, right? So these are the two functional requirement. The other thing, after booking a ride, our ride request goes to driver, so driver should be able to accept or reject ride request, right? So driver should be able to accept or reject the ride. Many of the time we have seen that when we request a ride, driver gets a pop-up on his window with a timer like 15 second. If he need to accept, if he want to accept a ride, he need to click on accept within 15 second, else it will hide from him and will be shown to different driver. So yeah, this is one thing. And the other thing is, after we are booking a ride, once the driver accept a ride, we are able to track him live. So drivers should be able to so drivers should be able to update their location so that we can able to give it to our user, update their location in real time. So yeah, this is the basically functional requirement that we want to cover. We will keep pick few things out of scope because we have a limited time. So first is, we won't cover multi vehicle, we are sticking with single vehicle right now. Multiple vehicle support, so yeah, this thing we are keeping out. Other thing is like rating for the driver and rider, rating and review, we are keeping it away in our system. So basically most of the system use rating and review in order to match the driver with the rider, right? So yeah, we are keeping it out of scope for now. So yeah, this is it. Now let's discuss about the non-functional requirement of our system. Before coming into the non-functional requirement, let's discuss about the scale of our system, right? What will be the scale? So assuming Uber and Rapido, they Uber like operates over the globe, so it have like daily active user of around 1 billion. Or for the simplicity, let's assume we are talking about Rapido kind of app, so it has a daily active users of around 100 million. Daily active users are there, and we can assume that every user goes to office and come back to him home, so at least each user is taking two rides a day, right? So we'll be getting two rides by 100 million users. This comes out to be 200 million rides per day. So the 200 million rides per day. Now converting it to the second, 200 into 10 to the power 6, this is for a day. Now converting a day into a second will be simply, our day has 24 hours into 60 minute into 60 second, which is roughly 84,600. So this will further boil, we can assume it to be a 10.5. So this is 2000 writes per second. These are the write requests that we can have. Coming on to one thing, that how many drivers, this is basically daily active user we are talking about. We have two entities here, right? One is driver, other is rider. So this is basically riders, we as a user who are booking ride. Coming on to the drivers, there are almost 6 million rider Uber have. We can assume like 20% or 25% of them are daily active user. So there are daily active drivers, there's a bad word dad, but yeah, never mind. So there are 2 million daily active drivers on Uber, and we want each driver to send their location update every 10 seconds, let's say. So every 10 seconds a driver will send a request. So 2 million driver, and they are sending 10 million requests per second. So like each 10 seconds they are sending their update request. So this comes out to be 2 million by 10 per second update, location update request, right? Yeah, location updates per second. So this comes out to be roughly 200k updates per second. That's huge. Our system is write heavy, we can see from here. Writes are much greater than reads. So this is the scale which will help us define our non-functional requirements. So yeah. So first non-functional requirement is our system must be highly scalable in order to support 100 million daily active users, and highly scalable to support 100 million plus DAO, right? Second thing is our system must be highly available. We are considering availability or consistency here, because we want our app should be up 24/7 entire globe, across entire globe. We don't want any downtime here, so 99.9% uptime we require. The other non-functional requirement is low latency on updates. Like what I want is my rider should be able to see real-time location updates from the driver. So low latency location tracking, you can say it. So yeah, this is one of the requirement. Latency should be pretty low. So yeah, this is pretty much, we are good with functional and non-functional requirement. Now what we will do is basically we will go into few more details about the entities and APIs. So we're basically following the pattern of functional requirement, then a non-functional requirement, then we will try to identify the entities in our system, then we will try to write the client facing APIs, then we will go through the high level design which will satisfy our functional requirement, then we will extend our high level design which supports our non-functional requirement. This is a good flow that we can follow in our system design round. Yeah. So the next thing is basic core entities in our system. Core entities are basically the data models that our system must have. So the first thing is obviously a user, but here two types of user are there. One is rider, other is driver, right? The other core entity is a ride request itself. The one thing is we can have is a vehicle. Other thing is location. It can be a location update event, we can say location update event or something. So yeah, these are the core entities that I can think of it right now. These are basically the nouns that are present in our functional requirement. So user is one noun, pick up and drop off location is a noun, ride is a noun, drivers, riders, and yeah, this kind of thing. So these are basically the core entities that our system must have. We will update it as soon as we develop and we as we are designing and we find out something else, so we can add up here. We can always go forth and back during our system design round. So yeah, now coming into the APIs part. What all APIs our system must have? Coming on to the first API is user should be able to get the estimated fare, right? So first API is get estimated fare. So this can be a get request as well as post request. So I will try to make it a post request. Why, I will tell you. So we will try to have versioning in our API slash. So in future, if we are upgrading to something else, we always have a backward compatibility in our system. So API slash v1 slash request write. Yeah, get estimated fare. Estimated fare. And the request body will be, we should define these things clearly in our system design now. So the estimated fare, the body will be simply the pickup location, which will be further and which will further be a JSON of latitude and longitude, and same we will also have a drop off location, which will again have the same latitude and longitude. So yeah, this is first the get estimated fare. Why this is post request I am creating is whenever a user will try to get the estimated fare, we will create a ride request then and there, and whenever a user is actually requesting a ride, we will try to update it. So you might argue with the statement, what if I am just checking the estimated fare and not booking a ride actually? So it won't get a problem as in future we can use the same data in order to enhance our pricing algorithms, like how we are calculating the price and all. So we should keep this data into our DB. So the next thing will be request a ride. So whenever a user will request a ride, we will try to update the same thing that we created into our post request. So this will be a fetch or a put request. Again, we will try to follow the same method of versioning. So request, we can say it a write request API. You might be considering why I am not passing. So yeah, whenever you will create whenever we are going to call this API of get estimated fare, it will give us few of the ride requests. What will be the output, you must ask right here, what will be the output of this? This will give us a few ride IDs. As we are creating ride here, so ride IDs, we can create, we can select any of this. So I will call it a partial ride objects and the list of this, right? While list, we might have a multiple options of either select auto, bike, but we are not supporting it in our system, so we can simply pass a single ride object to get a auto itself here, right? So this will be a partial object. Why? Because our ride request will be having a multiple things. So let's discuss this here. What all things our ride will have? It will have basically a ride ID. What all things our ride will have? It will have a ride ID. It will have a rider ID who is basically requesting this ride. It will also have a driver ID, and this will be optional because at the time of creating a ride, we know we won't be having that driver, right? We will now, after requesting a ride, we will try to match it to some driver and then it will update the things. So we will also have a fare here. Other thing that we will have is basically the location, the pickup and drop off. Pickup and the new thing will be drop. We will try to go into details when we are designing our database. So yeah, so these are the two requests, and what it will simply give us a ride ID, so we can get every details from our database, what all details that ride ID have. So the other thing will be this will be the driver facing API to accept or reject a ride. So this will be a simply a post API slash v1 slash uh, accept or reject ride. So the body for this will be simply, in the query parameter we will itself have ride ID. So in the body we just need to pass accept true or false, right? You might be thinking why we are not passing user ID in any of our APIs. So we should keep for the security purpose, we will pass the user ID into our headers. Now the next request will be of location update. We will try to make all the APIs which are client facing, basically which satisfies our functional requirement. So for the location update, we will be simply have the post API. Yeah, we don't have a get API anymore. So the post API will be simply API slash v1 slash location update. Each time the driver, again we will pass the driver ID into header, and here driver will simply pass his current latitude and longitude, which we can use to show the real-time location of the driver to the rider, right? So these are basically what we have, the APIs which satisfies all our functional requirement. So yeah, now coming on to the most interesting thing of our system, that is the high level design. So initially what we will do, we won't go into in-depth here, we will just try to make a system which satisfy all our functional requirement, right? Then only we will go into deeper and try to satisfy all our non-functional requirement. So yeah, let's go. So what we will be having is the users, which are there are two kind of users now we have. One is the driver and other is the rider. So here we have the rider and the other side. Yeah. One is the rider, other will be drivers. Whenever they will request anything, whenever they are trying to access a server with any request, they must pass through an API gateway in between. The role of API gateway is basically to authenticate and authorize the request, to route the request to the correct server. We can also implement a rate limiting here itself, so that user won't bombard a server with too many requests, right? So yeah, this is the role of the basic API gateway that we have. It can be AWS managed API gateway. So now we will try to follow microservice architecture. Reason being, we can scale our services independently, right? So the first service that we will be having will be, let's say, a fare estimation service. Fare estimation service. The other service that we can think of is a ride matching service. The sole role of this service will be to match rider and drivers, ride matching service. One more service that I can think of is a location update service. The role of this service will be to take the driver's location and update it into a database and real time update the location of the driver to rider as well, right? Rider service, location service. So yeah, now coming into the flow of our system, now we will also have a database here we will have a two database here. One is for the ride database, rides DB, where we will be storing all the rides here, and the other database that we will have is the location database. One is location DB. We will discuss about the type of database and all the things in detail. First we will try to satisfy a functional requirement, as simply as possible. So yeah, whenever rider requests a ride, first thing he will call for the getting the estimated fare. So the request will go to fare estimation service, get estimated fare based on pickup pickup and drop off location, pick and drop location, right? Yeah. So based on pickup and drop off location, it will try to get the estimated fare. Now how our system will be trying to get the estimated fare? So we will try to use an external mapping service, let's say Google Map or something, to get the ETA for this purpose. This will call the external service, let's say Google Map, third party service we can call it, third party map service, which will gives us basically, we'll call it to get the ETA based on the drop and pickup location. So ETA it will give, based on that ETA we can use the internal algorithm, our own algorithm, to derive the price. That can be simply, whenever we sit in the auto, there is always a base price of 26 rupees, right? So we can derive, let's say, how we're going to derive the fare, which can be simply the combination of base fare, which is like it, you must give this much, then we can have the distance, total distance, how much distance is there, and the per kilometer price, per km price, we can multiply it. Also we can consider a factor like the time of the ride into something like the per minute charges, per minute per minute price or cost, right? So we can have something like that. In order to fare, we can update it based on the, we can have multiple option, like based on the distance, based on time, based on the riders reviews and ratings. If he's a good driver, he's a safe to go with, we can give him a higher price or something. If, yeah, based on various factor we can derive. We can also use the search prices in order to check the current traffic, what is the traffic in that area, and we can increase or decrease the price accordingly, right? So this is there. So whenever we'll try to access the flight, we'll try to estimate the fare based on various algorithm, and we'll try to create a ride at a time and update into our ride database and give the ride IDs to the riders then and there, right? Now the rider have a choice which ride he want to go through. Let's say the driver selected this ride I want to go. Now this will go to our ride matching service in order to match it to a correct driver, right? Yep. In order to match it to the correct driver. Now this is a location DB that we can have. So basically location, instead of location we must have a driver DB. In itself we will try to update the location of the drivers itself, right? So we will be having a driver DB and the rider DB, rides DB. So whenever a ride matching comes, it will try to go with the driver DB and check all the nearby driver. We can have a various algorithm. We can either have a nearest drivers which are presented to the vicinity of the rider. Based on the drop or the pickup location, we'll try to find the nearby driver into a certain radius, let's say 5 kilometer, and try to assign them, try to send them a request. Then then the driver have a choice to accept or reject a request, and based on that we can update the rider. So basically here the driver DB will be called and find the nearby driver, and will be sent the rider that your ride have been matched. We will discuss about this in detail later. So yeah, now one more service that we have is a location update service. So drivers will be constantly sending their request at their location update every 10-15 seconds, right? So if we are sending the request too frequently, so the one of the best thing is we shouldn't go with HTTP. Why? Either our server will be bombarded with too many requests, right? We have already discussed it here. There will be 200k updates per second. That's huge in order to handle it. So one of the better solution that we have for this is we should use WebSockets. Yeah, we can also, there are many. So why WebSockets? Because WebSockets are a bi-directional duplex connection between server and a client. between client and a server, right? WebSocket. This will be basically a WebSocket connection. Now coming on to the gateway, we can use a layer 7 gateway, same as the HTTP, because many of them support the WebSocket connection as well. But since we are going to have a 6 million drivers, so the number of WebSockets will be too high. So recommendation will be go with a separate layer 4, which is basically a TCP based WebSocket API gateway. So it's always better to use that gateway. So we'll go with that. Yeah, after now driver will be updating their location too frequently to our location service, then we will update our database with this one. If we are sending this much request directly our database will be bombarded with too much request. So we need to decide the database accordingly, right? So yeah, this is the total. This system basically suffices all our functional requirement. Is the user able to get the estimated fare? Yes, he can call our fare estimation service and get the estimated fare. User should be able to request a ride. Yes, user is able to request a ride. Driver should be able to reject a request or a ride. Yeah. So from here we will be sending a driver a real-time request. This should also be a WebSocket connection between a driver and a rider. So rider should be able to accept and reject a ride from the ride matching service. This will also be a WebSocket connection between our ride matching service and a driver. Now driver should be able to update their location in every 15 seconds. Yes, driver are able connected to our location service, our WebSocket gateway, and updating their locations here. So yeah, this is pretty much it for our basic HLD, which satisfies our functional requirement. Now coming on to the scaling problem, how our databases will be, how our system will suffice this much request. So yeah, we will go into deeper into that section. Coming on to the database choices, as we discussed earlier, the number of requests that coming into our rights won't be too much high. It will be simply, we have discussed how much it was. It was 200 writes per second, right? So yeah, 2000 writes per second. So Postgres database easily handle this much writes. So we can go with Postgres database here because it easily handles 2K to 4K QPS. So yeah, we should go with Postgres database. Now what all tables we will have, as we discussed, we first will be having a write table. What will be the schema of this table will be a ID of ride ID. Now we will also have a rider ID, we will also have a driver ID, we can also have the status of our ride, right? Our status of the ride is in progress, fare estimated, let's say fare estimated, this will be the enum, basically in progress, or finding driver, other thing can be started, in progress, and so on and so forth, right? Completed kind of thing. Other will be the fare of this ride that we calculated. Driver ID will be optional, like initially I won't have driver assigned, after matching only we can update it, right? And so on. We can also have metadata. Yeah, as we'll go through, we will try to update this if we have come with more entities and all. So yeah, this will be the right table, the rider. Now coming the other table that we will be having in our database, this database will be the rider table, which will basically contain the detail about the rider. So which will have the rider ID, we can call it simply an ID. It will have the rider basic details like name and all. Our ride must also have the pickup and drop off location. Pickup and drop, I'm writing it in the one line, but we can understand due to space constraint. Yeah, pickup and drop location, this will basically a latitude and longitude. So this will be a rider table. The other thing which we'll be having is a driver table. What all it will have? A driver ID, we can call it ID and map it to driver ID to other tables. Driver name, one is driver's location, plus we shouldn't keep driver's location here, we could have driver status, like is he available right now, is he in particular ride, or is he offline, he is not available, like offline kind of. so that while sending a request we won't send him a request if it is in ride or is offline. So this will be our rider table, driver table and our ride table. So this is we go the Postgres database. Now coming into the driver database, as we discussed, like this will be a write heavy database, right? The number of writes will be like more than 250k, number of updates per second, so that's huge. So what we should do is we should go with write heavy database. Preferably I can go with Cassandra is write heavy database because it internally uses LSM tree in order to updates. LSM trees is basically first it try to updates in memory and then writes it into the SS table which are basically lying into our disk. So the write heavy database and it's easy to write here. So what all things our driver DB will be having is details about driver or location about the driver. So driver ID, it will have driver table, let me call it a driver ID, the name of the driver, the latitude of the driver, the longitude of the driver. We won't be having the status because we are already keeping it there. So yeah, this will be our write heavy database and will be the location for each driver. Correct? Yeah. So our system now will be able to handle this much request. But should we bombard our system with so many requests? What do you say? No, right? So we will see how we can fix that. Now coming on to the non-functional requirement of system. Is our system highly scalable? Yeah, since we have microservice architecture, so we can scale our services horizontally. Not an issue. Yeah, so we are able to scale our system. Is our system highly available? Yes, our system is highly available. Coming on to the low latency location tracking, are we able to track the location at the pretty low latency? I guess no. Why? We'll discuss about the ride matching now in detail and then try to satisfy that location. Now when a ride is request, let's say a rider is requesting a ride, that I want to go via auto, and yes, click on that. Now our algorithm will now our service will try to match it to the correct driver. What it will do, it will try to go into a DB, it will try to find all the nearby to the driver. How we will find it? If we are having the database, let's say Cassandra or MySQL in that place, this is not read optimized, right? So we shouldn't go with this. So since we are maintaining a latitude and longitude out here, so even if we are using, let's say, not Cassandra, since let's say we are going with Postgres database, then what are the downfall that we can have? First bottleneck is obviously the write request. Since our database is write request, so it will be a bottleneck for our system. How many requests per second we have is 200k updates per second. So for 200k updates per second, we will be having the write bottleneck in our system. We can solve this with the help of batching, but it will introduce a significant latency in our system. So the driver location won't be real time, right? So it will introduce a latency. So that's a bad solution. The other problem that we have is whenever a ride matching service trying to query our PostgreSQL based on the latitude and longitude, it will be too slow because we have millions of drivers out here, and scanning millions of drivers based on latitude and longitude will be too slow. You might argue that we can index it on latitude and longitude. So Postgres indexing is basically on the B tree, so they are mostly very good on a single column indexing. They work pretty good on one indexing, but here we are having a two indexes, so even though we are able to optimize a query, but it will be again too slow because it need to scan to millions of drivers again, like thousands of drivers again. So it will be pretty slow. So we should come with a better solution here. So one thing is we can think about is a geohashing, or like geohashing is basically a concept of how we can find the nearby drivers into our surrounding. So what we do in that is we divide the world into 4 equal parts, and we keep on dividing each of our segment further until we find out the correct location. We can find out the correct location. So this is how it works. So I'm like going into a brief overview. I'll attach a link where you can go through it into a detail. So it keeps on dividing the earth into equal part, and it, let's say this is 0. I'm just trying to call our earth, dividing it into a 4 equal segment, 3 and 4. Now it will further divide the fourth section into further 4 parts. So 4 0 we can call it 4 1, 4 2, 4 3, right, and so on and so forth. As we are dividing the earth into 4 segment, our segments are getting smaller and smaller. You can consider it like that. First our earth is, we call it earth, then earth is divided into countries, then countries divided into states, then states are divided into cities, then cities are divided into village, and so on and so forth, right? So at a particular point of division we can clearly pinpoint the individual location after certain partitioning, right? So yeah, so this is basically how we do it. So what is basically the concept that I am trying to tell is, we can convert our two-dimensional latitude and longitude into a single dimensional geohash. So there are plenty of algorithm that we can use to geohash our lat long into a single string, right? So now we can index our database into a single. So Postgres gives us an extension called PostGIS. So it does the same thing. It converts lat long into a geohash string and try to optimize a query. So PostGIS extension we can use, but still we are able to optimize a query with the help of PostGIS extension. But one problem that we are still having is the number of updates. And if we are introducing a batching, let's say I am waiting for 200 updates and try to split it into 50k and try to update our DB into 4 batches, right? That will still be high. So we need to batch it like into a 2k 100k batches, 100 batches of 2k requests, and then try to update it. So it will be slow. We need to enable a queue here, we need to have a queue here, then our request will go into the queue in the batches and try to update our DB. So it will be too slow, like our location won't be too much accurate, right? So we can't go with this approach. So the other thing that we can use is, instead of Postgres, what we can do is we can have an in-memory thing. Instead of using the DB, Postgres and all, what we can have, the structure will be same. What we can have is a Redis. Redis gives us a geohashing feature. It internally hashes the latitude and longitude into a string, and Redis can easily handle like 100k to 1 million QPS. Easily it can handle it. Based on, we can apply certain strategy of dividing into different nodes in order to maintain this. But yeah, we can easily handle 100k to 1 million QPS easily. So this serves our purpose. So we'll be storing simply what will be our key into, since Redis is a key value pair, and one more thing, it is a single threaded. So what our key will be, it is basically a key value store. Our key will be simply a driver ID, and it will have the geo hash for the driver, right? So yeah, it will be easily handle our request. So when our ride matching service trying to request our Redis, it can respond immediately with the driver near our vicinity. Or what we can have is a better thing is geohash, and all the corresponding drivers into that geohash we can achieve it via Redis sorted sets. So it will keep the geohash into the sorted order, so our query will be very much optimized, right? Correct. So this was the issue with the Postgres, but now we have solved it with the Redis. So yeah, this location update problem is pretty much solved. So yeah, we are pretty much done with our system design. Yeah, we can always go, and yeah, this is a pretty much good solution to have in the system design round. So yeah, thank you. If you have any doubt, feel free to comment and we can discuss it there. So yeah, bye.